before I get started, help me settle one thing, okay? I'll ask for you to raise your hands, all right? So, in the month of April, okay, so we are almost done with the month, who here has used a coding agent, any coding agent to help you code? All right. No, keep your hands up, keep your hands up. If it gets too tiring, you can swap hands, that's allowed, but keep it up otherwise. All right. Who thinks that, if you think that more than 20% of your code was written by code agents, keep it up. More than 20%. Of the code that you commit, whatever, right? Of the code produced by your machine, George. So everybody understood the question. Okay, more than 20%, all right? More than 40. More than 60. More than 80. Okay, I won the bet pretty clearly. All right, thank you very much. Okay, this is not related to my talk at all, but thank you for entertaining me. Wait. Yeah, you didn't raise your hand, right? If you didn't use AI tools, yeah. Yeah. We good? All right, let's get this party started. So today I'm going to talk about precision in type system design. And the reason I wanted to give this talk, I have been thinking about this for a while, is because since, what was it, Guillaume, 3 years ago that we announced? 3 years ago that we announced the type system before, 3 years ago? You probably heard me talking, and like in the official documentation, you probably heard me talking about precision, right? This word is coming up, precision. What does it mean, like, to have precise type signatures and precise types? And that's what I want to focus on most of this talk, and then we are going to talk about the next Elixir version. And in order to talk about precision, we are going to explore this example. Folks in the back, can you read the example well? Oh, good, because I didn't have a plan B. All right. So this is the code example that we are going to work for most of this presentation today. It's very simple, but it's very powerful to show the things that we want to talk about. So the goal of this function is that it's going to receive a binary, right, a string, and it's meant to return the largest word in a string. So if you have the string there in the comment, like foo, comma bar, comma bass, comma etc., it's going to return bass because it has 4 characters, right? String length is going to return 4. So what we do is that we receive a string, we split by comma, that is going to return the parts of the string, and then we call a num max by. So we want to get the part, we want to get the word that has the biggest amount of characters, right? That has the biggest length. So we know that max by is going to raise if you give an empty string, right? So, max by is going to raise if you give an empty list, right? Because you can't get the maximum of something that is empty. So if you give an empty list, it's going to raise. And my question is, can this function raise at runtime? Feel free to say yes or no and tell me why. Can this function fail at runtime? If you give it a string, a binary, it's not a tricky question. If you give a string or binary, can this function raise at runtime? Yes. Okay. So it cannot. And the reason it cannot is because string.split, by guarantee, it returns a no-empty list. Okay? If you give an empty string to a string.split, it's going to return a list with the empty string in it. So parts is a no-empty list. So because it's a no-empty list, right, we are going to give a no-empty list to max by, and max by is always going to give a result. Okay? So this function cannot fail at runtime. But the question is, can our type system actually understand that? Can we write our types in a way that they are going to be precise enough that the type system understands that too? Or the type system is going to think, no, I actually think that can raise, and you have to deal with this scenario. So in order to answer this question, we are going to consider 2 possible type systems. One is a type system that cannot distinguish between empty and no-empty lists, right? And most type systems, they are like that. They have a list type. You can say like list of binaries, list of strings, and it doesn't tell you anything about if that list has 0 elements or it's not empty, more than 0. Okay? So if we have this type system that cannot distinguish between empty and no-empty lists, so if we look at max by, we'd probably have this function signature, right? We'd have something that, okay, I have max by that receives a list of A. So A means a list of something. We don't know what that is. It can be a list of integers, a list of binaries, a list of lists, right? So it receives a list of A, and it also receives a function that is going to receive the A, is going to receive the thing inside the list. It has to return an integer so we can get the maximum, right? So we can sort it and get the maximum one, and it's going to return one thing from inside that list. But if this type system that for this programming language cannot distinguish between empty lists and no-empty lists, there is an issue with this function in that this function can actually raise at runtime, but the type system cannot tell you that it's going to raise at runtime, right? So if you are designing this function, you may think, no, I actually would prefer to have something like maybe max by, because if you give me an empty list, I'm going to return the atom empty. And if you give me a no-empty list, I'm going to return OK A. All right? So the idea here, what is happening is that because the type system cannot make a distinction between empty lists and no-empty lists, now we are pushing, like, we cannot express that in the type signature. So now we have to use like these result types, or we need to start returning tuples and atoms to make a distinction that the type system cannot distinguish. Does that make sense, right? Like the type system cannot tell us, cannot say what is an empty list from an empty list. So now we are pushing that verification somewhere else, like to the return type of max by. So let's go to our function, right, that we started with. We're like, okay, our type system cannot distinguish between empty lists and no-empty lists. So what we are going to do is that we are going to call the maybe max by, right? So we call the maybe max by with a case, and then if it returns OK part, right, it's because we gave it a no-empty list. But if it returns empty, it's because we gave it an empty list, right? And therefore, we need to do something. What do we do in this case? We raise, right? Because we know, like, it's not possible. We know that string.split, right? It's always going to give a no-empty list, right? Therefore, the branch, the empty branch, is never going to be reached in our code, right? There's nothing we can do. Like, it's not supposed to happen, right? So we're just going to say, look, we raise. This should never happen, right? Like, just raise never. Right? So again, because the type system cannot distinguish between empty lists and no-empty lists, now we are moving these checks all to runtime, and now we raise. And this is not a problem specific to Elixir, like this theoretical Elixir. Like programming languages, typed programming languages, they have unwrap, they have assert, they have raise, right? And the issue with this is that unwrap, assert, raise, they are encoding invariants such as string.split returning a no-empty list. We are encoding variants in the code that the type system does not verify nor track, right? So the whole idea here is that we are saying, look, our type system cannot distinguish between empty lists and no-empty lists, but no-empty lists, they are going to happen as part of our program, but the type system doesn't know that, so now we are raising and doing things to deal with that thing that should not happen. But anyway, let's say that we are happy with this code, okay? So we get that code, right? We ship it to production, and then time passes, and we decide to refactor, okay? So what we do is that we break that function into, right? It's the same code as before, but just broke into functions, same functionality, I mean. So what we have now is that we have largest word from string, and what that does is that it splits the string on the comma, right? And then we call max word that is going to call enum maybe max by, right, and do the code as before, and it's going to raise, right? And you know, it could be a typed language that can do type inference, and then it knows that max word can work with lists. But again, like it's encoded in max word that you are supposed to give it a no-empty list. It's just that the type system doesn't know about it. So what happens in the future is that when you introduce this function here, largest non-empty word from string, which gets the string, splits it, but removes empty strings from it. Now what is going to happen is that, yes, we can now give an empty list to max word, which means that the code that the empty branch, now it can raise at runtime. It can fail, but the type system is not going to tell you that, because by definition, the type system doesn't know the difference between empty lists and no empty lists. So now you have a runtime bug, a bug that is going to happen in production, and your type system did not tell you about it, right? Because it's a type system that is not very expressive. It cannot make the difference between empty lists and no empty lists. So we cannot define precise type signatures to our code. And therefore, when we start adding the unwrap, the assert, the raise, things can now go wrong. So far, so good? But what if we have a type system that can distinguish between empty and no-empty lists? What is going to happen? So the first thing is that, so again, we go back to our starting code, the largest word function. So what we're going to do is that now when we define the type signature from max by, this is the type signature we're going to define. So first, we are going to say, well, when I say list of A, it means it's a union between an empty list or a no-empty list. So now we are making it more expressive, and now we can have more precision. Because instead of list of A being just this thing that cannot break apart, we're like, look, list of A, now we can distinguish between empty lists and no-empty lists. So when we declare the type signature for max by, we are going to say, hey, this thing can only work with no-empty lists, right? So if you give an empty list to it, it's going to raise, because the type signature is saying that it only works with no empty lists. So we can keep our largest word function exactly as it was, right? We don't have to change anything. We are happy the type system is going to know that string split returns a no empty list, and we give a no empty list to max by, so everyone is happy. And then when we refactor the code, we break it into functions, largest word from string, and max word, everything's still going to work fine. The type inference that we have in Elixir for today is going to know that max word can only work with no empty lists, because max by can only work with no empty lists, right? So everything's working beautifully, right? And then when we add the largest no empty word from string, we are going to get a typing violation, because the type system can track what is an empty list from a no empty list, and it's going to figure out that we are trying to pass an empty list to max word, and max word only works with no empty lists. We get a typing violation. And now we can fix it, right? We could say, okay, so if reject gives me an empty list, now I'm going to match on the empty list and do empty, otherwise I call max word, right? So because our type system is more expressive, we're able to define a more precise signature for max by. Max by could say, I only work with no empty lists, right? And now we don't have those bugs lurking behind, because the type system can understand more about our programs. So this sounds good, right? And then you may be thinking, let's make our types as expressive as they can possibly be, because now we can add precision for everything, right? That sounds like a good idea, right? But is that such a good idea? Let's make our example a little bit more complex, okay? So we are going to add a new function called largest word from last 10. So the idea here is that we can give it a large string with things separated by comma, and we want to get only the last 10 words and get the largest from the last 10, okay? So what we do is that we call string split as usual, and then we call parts. And what we are going to do is that we want to drop everything but the last 10. So we get the size of the list, we take 10, so we drop everything, and we remain with the last 10 here, okay? So what we do is that we get the list, drop everything but the last 10, but if the list has fewer than 10 elements, we don't drop anything. So that's what that line is doing. So I get the length, subtract 10, but if the length minus 10 is negative, I say that the maximum is 0, so we don't drop anything. Can this function fail at runtime or no? No, it cannot fail, right? Because we know that string split returns a no-empty list. And we know that we only drop things from the list if it has more than 10 elements. And we only drop what is over the excess, right? So this code cannot fail at runtime, right? Because we are always working with no empty lists. But the question is, now when we call maxword, is the type system smart enough to know that it cannot fail at runtime? Or the type system is going to say, wait, you are potentially calling maxword with an empty list, right? Although we know at runtime that's not possible, right? But the type system may think it's possible. And the reason why the type system may think it's possible, because if we look at the type signature for drop, this is a very sensible type signature, right? We say, look, if you give me an empty list, it doesn't matter what you ask me to drop. It's an empty list, so I'm going to return an empty list. That's sensible, right? But if you give me a no empty list and an integer, I may return you an empty list or a no empty list, right? So drop, when you give it a no empty list, the result, if it's going to return an empty list or a no empty list, depends on the integer, depends on how many things you're going to drop, right? And right now, our type system is not expressive enough to tell us if it, to say, oh, if you drop nothing, if you drop 0, you are going to get the same result back. So the type system cannot do that. Right? So if we go back to the code here, what is going to happen is that even though this code cannot raise at runtime, the type system is going to think, because even though it can distinguish between empty lists and no empty lists, the type system is going to think, oh, I can give, maybe an empty list is going to appear in max word, right? Even though it cannot happen, the type system is going to say, maybe it can appear, so you have to check for that. And we have to check for that and raise, right? Raise never, right? Because at runtime, it doesn't happen. So here's what I'm going to do. So basically, we start with that code. We now have a more expressive type system that can make a distinction between empty lists and no empty lists. But it's not enough we cannot type the drop function with enough precision, right? We need to make the type system more expressive. So here's my idea. What if we break integer into 3 types, right? Let's say that instead of integer, we are going to have negative integer, or 0, or positive integer. Okay, so we broke it apart a little bit. And now that we did that, maybe we can add this type signature to drop. We can say, look, if you give me an empty list, it doesn't matter the integer, I'm going to return a no empty list. But if you give me a no empty list and you ask me to drop 0, to drop nothing, I'm going to return a no empty list, right? Because if I have a no empty list and I drop nothing for it, I continue with a no empty list. But if you give me a no empty list with an integer that is not 0, then I'm going to return you a list that may be empty or not. So far, so good? Right? So we are adding features to our type system, or make it more expressive, and now we can define those more precise type signatures. That sounds good, right? So, okay. We may drop more expressive, more precise, sorry. We may drop more precise because now we have 0 in the type system, positive integers, negative integers, but now we have to make max more precise, right? So we have to make the whole code, all of the function signatures more precise. So you can think, okay, let's make max more precise now that we have those, now that we can break integer apart. So the way we do that is that we go to max and we say, well, if you give me a negative integer and a negative integer, I'm going to return a negative integer. But if you give me a negative integer with 0, I'm going to return 0. But if you give me a negative integer with a positive integer, I'm going to return a positive integer. And there you go, right? So we start to see what is the problem, right? We are making the type system more precise, more expressive. And as a consequence of that, we can make things more precise. But now our type signatures, to capture all that precision, right? They are starting to get more and more complex. And then the error messages, they're going to get more confusing, and the code is going to get harder to debug when the type system, when type checking fails and you get a violation, right? And we didn't even get to length, to type length, which would require some sort of dependent typing. So the point that I want to get here is that when we are thinking about type system design, we have like this, we have to choose between like simple versus expressive, but there is no clear answer. There's like no silver bullet. There's like no best choice, right? Some people want to say, hey, we have a very simple type system, and that's great, right? But we saw the issue with simple type system is that by definition, they cannot capture many properties about your code, so you have to move assertions to runtime, which by definition the type system cannot understand, and then you can have failures behind that code because the type system is not expressive and we cannot write precise function signatures. But if we make the type system very expressive, right now there's a lot of complexity that we can model, but our type signatures, they start to become very complex. Type checking is probably going to take longer, right? So we often hear like different programming languages say, hey, a simple type system is great, right? Or, oh, this type system is very powerful. But there are like trade-offs in that they are not like, they cannot go away. They are inherent trade-offs, okay? And so there is this whole discussion, right, on how simple and how expressive we can make a type system actually being practiced. And we are going to come back to this. But there are also two conclusions that we can take from this discussion that I think it's very important. So if this all sounds like a little bit too much, right? There are two things that are very important that I want you to keep in your head, okay? The first one is that type systems do not mean error-free, okay? As we were talking about, right? Like if you have a simple type system, what is going to happen is that we have to say, look, the empty case is never going to happen because the type system is simple, cannot fully understand that code, right? And then when we refactor the code, what happened, right? We had runtime errors, right, that were happening behind, even though it's a typed language, right? So for most mainstream languages have runtime errors, and those errors are not tracked by the type system. Do we have languages that can track exceptions? Yes, we do have languages. Do we have languages with very expressive type systems? Yes, we do. Can you get Rust, remove the standard library, and use linter so it never unwraps or expects anything? Yeah, you can do that. But most mainstream languages, okay, they have runtime errors, and those errors are not tracked by the type system. So if you get the majority of programming languages, and you write software saying, look, my programming language has no runtime errors, what is going to happen is that that's a lie. That's not true. Your programming language is going to have runtime errors. So you're going to write your code thinking that it has no runtime errors. And then when something goes wrong, when one of those invariants happen, you end up with a global outage, right? So we have runtime errors. That's true for most mainstream programming languages, right? So it's very important for us when we have a type system. I believe I talked about this when we first announced the type system. When we have a type system, if we get this attitude, oh, my code cannot fail anymore, we are going to end with worse software, right? So for us, it's very important that even when we have types, for us to remember to continue to write code that is fault tolerant, that is resilient to failures, right? So when we're talking about types and exceptions in Elixir, exceptions are not going to be tracked by the type system for now, as in most languages. So that's not a goal for now. Maybe it will change in the future. But for now, that's not going to happen. And we should continue using our tools for local reasoning about exceptions, like try rescue. And we should continue applying Erlang OTP principles for fault tolerance. Okay? The other thing, so that's one conclusion, right? Like type systems do not mean error-free. The other thing that is going to be very important as we continue to add types to Elixir is to say that type systems will always reject valid programs, right? So when we look at this code, even though we made our type system expressive to have no empty lists and empty lists, when we give this code to the type checker is going to say, hey, there is a typing violation. Max word is going to receive an empty list. But we know at runtime it's not possible. We're like, what are you talking about? I know, like, I run this code. There is no argument that I can give to this code that is going to raise at runtime. But the type system will think that there is an error. It's a valid program, but the type system is going to reject it, right? Because we can, even if we made it expressive enough to solve this particular problem, there's always going to be a program that the type system is not going to be able to fully verify, right? So there are going to be cases when we start adding type signatures. When we release the type system, we start adding type signatures to your Elixir programs, that you have to do things like that. You're going to say, hey, never. This branch is never going to happen, right? Because the type system is not expressive enough. It's not going to allow us to write the function signatures with enough precision. So that brings us a question, which is, well, we have millions of lines of code of valid Elixir programs today. So how can we type them without those false positives? How can we type all the code that we have today, right, without the type system saying, hey, I think there is an error here. When we look in depth, we're like, no, that error cannot happen. So the way we have been doing this is with gradual typing, all right? And every time I talk about gradual typing, I talk about the dynamic type, and I say how the gradual typing in Elixir is different from gradual typing in the huge majority of other programming languages, right? And now I want to show you a more precise example of exactly what I mean by that, right? So let's go back to this code, right? This code that we are struggling to type, right? So largest word from less 10, so we split this string by comma, we have the parts, we remove everything but the last 10 elements from the list, right? And we get max word. So the reason why we are going to get a typing violation in this code is because we are calling max word with a list, but we know that list is empty list or no empty list of A, and we also know that max word only works with no empty lists, right? So because we're trying to give an empty list to it, the type says like, no. You're telling me that you can give me an empty list, but I only work with no empty lists, so I need to emit a typing violation. So the way that the type system works is that if you can give it something that may fail, so we can give it a non-empty list, and give it a non-empty list is work, but because we're saying that we may give it an empty list, the type system is going to say, nope, I cannot accept it. By default, type systems, they need to accept all the inputs. But the thing with the dynamic type is that if we wrap this type, empty list or no empty list in dynamic, what we are going to say is that, look, the call to max word is only going to fail if all of the types that you are giving is not allowed, right? So it changes the semantics to be, instead of the call to max word failing, if any of the types do not match, it's only going to fail if all of the types do not match. And this is exactly how, for the last 3-4 Elixir releases, I say, look, we are improving the type system, and you are getting bug reports. And I say, we're only getting certain bug reports. Those are bugs for free. Because what we do today is that the type system only emits a typing violation if all the types that you are giving to a function are invalid, right? And that's thanks to the dynamic typing. So what we are doing is that we are adding the dynamic type everywhere for you, for now, by default. So the dynamic type in Elixir avoids false positive warnings, right? Because it's only going to fail if all the types fail, right? If all the types are not allowed. And right now, it is inserted by default into Elixir programs, okay? However, in the future, when we have type signatures, and you put a type signature in your function definition, right? That is going to be a statically typed program, and we are not going to impose dynamic by default. So in the future, right, we are going to have those false positives because we'll stop putting dynamic on everything, right? And that's why I say that the dynamic in Elixir is different from the other programming languages, because the other programming language, dynamic usually means anything goes. They don't check anything. We are still checking. We are still checking that all the types need to be supported, right? The other cool property about dynamic in Elixir is that dynamic can still be refined by the type system. And what I mean by that is, so the way the type system in Elixir works is that, imagine that you write this very simple function, right? Int to a string, and all it does is that it calls integer to a string. So what we do to type check this function, we do something as if we said, look, let's just imagine that the argument is dynamic, okay? So we start type checking, assuming that the variable int is dynamic, but then we pass that variable to integer to string, and integer to string says, look, I only accept integer. So based on the information, we refine dynamic to be dynamic integer. Right? So what we do is that we start with dynamic, and as we type check your program, we are accumulating information about your program and refining your program. Which means that if we have this code, imagine that you say, I have this function, number to string, and then the same variable, you try to use it as an integer, and you try to use it as a float, you get a typing violation, because we refine the dynamic, and first you say, oh, the dynamic's being used as an integer. And they're like, wait, the dynamic's being used as a float. That's not possible. Boom, type violation, right? Which for other gradual type languages, many of them, this doesn't happen. When it's dynamic, it means it's dynamic. It closes, the type system closes the eyes, like, no, anything goes, anything can happen, right? We can still use the dynamic to refine and get important properties from our software. So to sum all this up, right, summing up for now, right, we talk about simple versus expressive, and that there is like no silver bullet, right? It's always going to be trade-offs. Those are inherent trade-offs, and we can't pick one and say, this is better. It's going to always have trade-offs. Type systems do not mean error-free. Type systems will always reject valid programs. And we use dynamic, for now, to find certain errors. Certain has a double meaning here. To find errors that, they are guaranteed to be there. It's going to be a bug. Okay, so for now, still when we are reporting violations, they are certain violations. They are going to happen. They are going to be there. So with this in mind, let's talk about Elixir 1.20. All good? You ready? All right. So in Elixir 1.20, we typed all constructs and data structures. So like all the constructs of the language, case, with, function application, everything Elixir can do, right? The type system understands, as well as all data structures that we have in the language. And what we have been doing, so this was, I think, maybe December last year or January this year that we achieved this, and we shipped the first release candidate for Elixir 1.20. And what we have been doing every release after is that we are working on improving precision, and I'm going to show you several examples. And we are also working on improving performance, both of the type system and the compiler. So generally speaking, we are getting reports that the compiler is twice faster in Elixir 1.20. But the Keynote from remote today showed that there is a new flag that in their case was 5 times faster, right? So this is great, right? So that's what we have been working on. So, and let's talk a little bit about what do we mean by typing all constructs and data structures. So one of the things that we do now is that we can gather information from guards. So if you have like this function signature, example x, and you say, tuple size x equals 3, we know that x is going to be a tuple with 3 elements. We don't know the type of those elements, but we know it's a tuple with 3 elements. If you say example x, and then you say the first element of x is the atom OK, we are going to say that x is a tuple where the first element is OK. We don't know the rest, right? It may have 0, so what the ... says, like, oh, it may have 0 additional elements, so it may be a 1-element tuple, but it may have 10 additional elements. We don't know. All the information that we have is that the first one is the atom OK. If you say that, example x has a map key, x is a map with the key foo, we know that the type of x is going to be a map with the foo key set to term. We don't know exactly what is the value in that key, but we know it has the foo key, and it may have any other keys, right? We don't know. It may have only the foo key, it may have 100 keys, but we know that it has to have a foo key, right? And we don't know what is the type of the value. We can even say that, it doesn't have the foo key, where we are going to say, well, so we have a map that may have other keys, but we know that foo is not set. So if you try to call this function with something that has the foo key, it's going to raise. You're going to get a typing violation, right? And then we do inference throughout the program, for example. So if you write this code, add full and bar, passing the variable x, we are going to say, okay, I know that x is going to be a map, and it has full and bar keys, and we know that we are giving them to the plus operator. Therefore, it means that those keys, they need to have numbers in them. So if you pass something with a binary in it, you're going to get a typing violation, right? Something that we have been doing recently, this is going to be in the next release candidate, which is going to come, not this week because it's Friday, next week, is this thing that we are now refining the type based on the clauses. So let me show an example. So imagine that you have this code, system.getEnv returns new or a binary, right? So that's what it returns, binary or new. So in the first clause, we look at the first clause and say, hey, can new match? And they're like, yeah, new can match. It returns binary or new, so new can match. If the first clause said like the atom OK, we would get a typing violation because it say, look, no, system.getEnv cannot return the atom OK. We would get a typing violation. But in this case, new, yes, that's a possible result. And then what we're going to say is that value has the type binary or new because we are matching on the type system.getEnv. And then we would call string.upcase passing binary or new. And then you would say, wait, José, string.upcase only works with strings, only works with binaries. If you give a new to it, it's going to fail. So we're going to get a typing violation, right? And no, for now we don't, because remember, we wrap everything in dynamic, right? But what we did in this, what we're going to do in the next release candidate is that we'll be able to refine the type. So this is what's going to happen instead. We start with system.getEnv, right, which is binary or new. And then we match on the first clause, which matches on new. So now we know that value can only be a binary, right? Because we took the new out, right? So it can only be a binary because we already matched on new. And now, when we call string upcase, we're only going to pass a binary, right? And then even if we didn't have the dynamic, type checking would work because we are understanding the programs with a lot of precision. We are refining the types. And this is a very good summary of the work we have been doing for the last 2-3 years, okay? What we did is that we started with like, everything is dynamic, okay? We start with everything in dynamic, but we're not getting a lot of exceptions because remember that things would only fail if all the types fail, right? So that's the idea. Everything was dynamic. And we started slowly refining, adding precision, adding expressiveness to the type system. So now we are at a point that even if we remove dynamic, the type system is expressive enough to say, look, we can even remove dynamic and we're not going to get a lot of type violations because the type system can really understand the flow of the program. All right? We even added occurrence typing. So for example, in this case, consider this example, system.getEnv, as we know, returns binary or new. So X is going to have the type of binary or new. But we know that in order to be in the do branch of an if, we know that it cannot be new or false. So inside this branch, we know that X is a binary, and inside this branch, we know that X is new, right? So what we have been doing is that we have been adding expressiveness and precision to our existing programs, right? And what we are doing is that our expressiveness is guided by existing programs. That was the goal since the beginning, right? When we started doing the research, we're like, we need a type system that is going to be able to capture a lot of the Elixir idioms, because otherwise, we wouldn't be writing Elixir, we would be writing something else, right? So our goal is to type as many of existing Elixir programs as possible because we like the expressiveness that Elixir has, right? But we have to remember, we will have false positives, right? Our integer type, for example, is just integer. It's not going to be integer, which is positive integer, 0, no negative integer, right? It's just integer. And in some cases, it means that we will not be able to write such precise definitions that is required to not have false positives. So, wrapping it all up, right? When we started this, we set some initial milestones. We first started with research, which we concluded. We announced the paper. Then, and then when research was done and we felt very confident that we can type Elixir with a good amount of expressiveness and bring precision to our code, we started development. And when Elixir 1.20 is officially out, we can finally say that we have type inference of all constructs, right? So we finished the first big development milestone. And remember that at the beginning, our goal was type inference of patterns and guards. That's what we started with. But as time went on, like, wait, we can do type inference of all Elixir constructs, right? And now that out of the way, we are almost ready to get started with type definitions and type destructs. And then we can finally talk about typed functions, behaviors, and protocols. And the reason I said almost is because there are still some blockers, right? So if your question, I got asked already a few times during the event, is like, is Elixir going to be typed, right? It's like, are we sure? Like, because in all my talks so far, like, we are not sure yet. We are working it, but we are not 100% there. And we are still not 100% there. There are some blockers. So the first one is performance. Every release, we continue assessing performance and we improve performance. Whenever we release a new release candidate for Elixir, we had a couple, I think we had 5 of them already. There will always be a program that could not compile. It would take too long to type check. And then we went and we fixed it. So we have been able to address performance every time it happened, but there may still be cases where the performance is really bad and we cannot make it fast enough. So if you want Elixir to be typed, the best thing you can do is to try the release candidates, the 1.20 release candidates, and give us feedback if you find anything that is not as fast as it should be. And if you don't want Elixir to be typed, the best thing that you can do is to also try the release candidate and find a program that we can not type check fast enough, okay? And then let us know. So one way or the other, please try the release candidates. But besides performance, and we're making sure that the type system can be highly performant, there are things that we need to do in the implementation, like within the type system implementation itself, which is to support recursive types. Because when we add type definitions, we need to support recursive types. And also support parametric types. We have to implement this in the type checker. It's not there yet. So earlier in the talk, when I did list of A, and A could be anything, could be like an integer, a binary. Those are parametric types, and we have to implement them in the type system. And after we implement them, we have to benchmark. We have to make sure they are fast. And something that we are still working on is typing of pairs. So what happens when you give a map to the enum module, like enum map, enum drop, enum filter? That's something that we are actually researching on how to do that. We don't have all the answers yet in this particular case. So we are even back to doing some of the research to try to address some of those potential blockers. And there are also some open questions that I don't consider them to be blockers. So for example, typing of processes. Since the beginning, I said typing processes is not an immediate goal for us. And the reason I said that is because most of our processes, they are behind behaviors, right? They are behind just servers, right? Supervisors, and so on, right? And that's also something that we are researching, right? We have PhD, postdoc students researching this. Because when it comes to behavior, we can type them as well as Dialyzer does today. We have that level of precision, but we are trying to see how can we make it more expressive? How can we make so we can write more precise programs? Okay? So in other words, we have been doing a lot of progress with 1.17, 18, 19, and 20. We are now typing the type system can now understand all Elixir constructs, all the data structures. We can type them with a good amount of precision. But for the next releases, we'll focus on the type system foundation. We're going to focus on those potential blockers and open questions. So with all that said, once again, I want to thank the companies that and institutes that have made this possible. So the type system is a partnership between the CNRS and Remote. Development is sponsored by Fresha and by Tidewave, which is a coding agent that we have from Dashpit, that me and the Dashpit team are working on. So go thank those companies, They are hiring often, reach out to them, use their services. They have been extremely important for to make this work possible and for all this progress that we have been doing, both in research and development. Okay? And there is a new spot to sponsor type system development. So if you're interested, reach out. That's all I had to share for today. Thank you very much. Hmm? Any questions? Yeah?
Okay. We're going to do questions. I only see one question in swap card, so please add some more to swap card for me. First up, Brian wants to know, would it be crazy to have a flag to allow people to turn off the default dynamic wrapping?
It is a good question, and we will have this flag eventually, but the thing is exactly like, until we make sure that the precision is really there, you're going to get so many false positives that you'll be like, oh, you know, so we need to get to a point where like, okay, there's a lot of precision in here. Not, you can have false positives, but it's not going to like overwhelm you.
Okay.
In the future, yes.
Thiago says, how will Erlang native records affect the type system?
So to give a bit more context, Erlang OTP 29, which is going to be the version coming in May now, they introduced this concept called native records. And I have been tracking the work, giving feedback. How that is going to interact with the type system, we don't know yet. So that's future work, not something that we, so we are following it, but we don't have an answer yet. We are going to revisit later.
Okay, thank you. Alrighty. I'm going to give it another couple seconds for anybody else to add any questions.
Yeah, you had a question, yeah.
Okay. Just a moment. Let's see. I'm not going to pass the microphone around. That's just why we do it in swap card, but you can tell us and then.
Okay.
Yeah.
So
I'll repeat the question. Don't worry.
So when our type system will get there in the future, that let's say there will be a part of code that there will be no dynamic. Our code will be inferenced, and there will be a case, as you pointed out, where the expressiveness is not enough. Will we be able to overwrite what was inferred using like custom typing?
So the question is, in those scenarios that we're talking about, where where we know at runtime that it cannot fail, but the type system thinks it's going to fail, can we override it? And I think the answer is, maybe Guillaume is going to have an opinion, but I can't see that being a good thing. In the sense that even if you override it, it still means that because if you say, look, I want to override the type system, it means that the type system cannot understand that program. And you overriding it is not going to make anything better. Like, there are two scenarios. You override it and you are right, but it still means that when we refactor and move things around, the runtime error is still going to be there. So that's not good. So you are overriding it, but you are encoding this invariant, overriding the types, and things are can still go wrong, or you're overriding it in the wrong way, which would be a bad idea as well if you override it with something that does not match the type system. So right now, like off the cuff, I may change my mind, but right now I can't see overriding being beneficial. I would prefer for you to maybe we'll make raise if it's so common that we are writing a lot of raise nevers in our programs. Maybe we'll figure out ways of doing that. That would be how I would first think about it, because yeah, like let's encode this runtime. Oh, sorry, let's encode this property in the actual program instead of overriding the type system. Thank you.
All right, Craig wants to know, I'm mildly obsessed with effects. Will we ever see types expressing totality or linearity like Coca?
So maybe in the future, but that's a very expressive type system. As we were talking about, like there are trade-offs that happens as consequence of those designs. And so maybe in the future, but it's definitely not a goal for now.
Alrighty, let's see. Alexander wants to know, can Erlang also benefit from Elixir experience with the type system?
Yes, because typing Erlang is very similar to typing Elixir. And even the work, so Elixir type system uses gradual set theoretic types. There are folks researching what is the name of the type system for Elixir, right? So it's also a type system based on gradual set theoretic types for Erlang, and like we are publishing. We publish new research. They use it. They publish new research. We use it, and yeah, it can benefit because Elixir is going the expressiveness needed for Elixir is a superset of the expressiveness needed for Erlang. Actually, the only thing that we have on top of Erlang is protocols. So typing Elixir is the same as typing Erlang plus protocols. So yeah, they could definitely benefit from this work, and there is collaboration happening already.
All right. Aside from the type system, Peter wants to know, aside from the type system, are there any other new features planned for Elixir?
So I believe there are some new features. So for example, one of the things that we have been doing is that we have been working on Tidewave, which is the coding agent for full stack applications, so for Phoenix. And we've implemented some tools that we know it's very useful for coding agents and for working with AI. And we have been bringing some of those tools to Elixir itself. So like we know, so for example, you probably use mix help, the name of a task, to get information from a task. But what you can do in Elixir now is that you can do mix help and the name of a module, and it's going to bring documentation from that module, or from a function, right from the CLI, which is very useful for agents to quickly grab information. We have also added like mix source, so it's very easy for you to get the source of a particular module. A lot of those things were extracted from Tidewave, and there are other features. So you can check out the changelog, where we keep it relatively up to date, so it's going to have a good summary of the features. But I think the biggest ones, they are 100% type related and making the compiler faster and faster. So yeah.
Alrighty, thank you. And let's see. Tim says, if you could go back and re-implement Elixir again, what would you do differently? In 30 seconds, go.
Yeah. I get asked that a lot, actually. And I never have an answer. I'm not going to, It's perfect. So there are definitely things. So the reason is like, it's going to become a therapy session now. So the thing is that I was used to think that myself, like, somebody would say something about the language, not necessarily something mean, it's like, oh, what about this? And I was like, oh, okay. So for example, what if parentheses were actually always required, as an example, right? But you feel like that's a small change, but it actually that change propagates through the language and changes so many things that even if you say like, look, I would change one thing, the effect of that change can be really big, right? Like, so for me, it's like, look, would I want to change something? But change something even if you think it's small, like parentheses, because that decision end up pushing other decisions to happen. You end up in a place where like, oh, I'm actually reevaluating the whole language now, and then that's no longer Elixir, right? And for the smaller things, or that we're like, oh, could this be better? Could this be different? We the language is still changing, right? So if you figure out that, oh, we don't like that, we like to do different, we introduce the new way, we deprecate the old way, and we move forward.
All right. Joe Henderson says, does typing improve JIT somehow? Maybe after refactoring code?
Does typing improve JIT somehow? No. So the answer right now, it's a very easy no. Maybe in the future when Erlang has, so imagine that the type system works out for Elixir, everything's doing great. Erlang says, hey, we want that too. Then we work together with Erlang to add the type to Erlang. Then by that point, they can potentially start using that information within the JIT, and we can leverage that. But right now, performance is not a goal.
Alrighty, thank you. Let's see. Alfonso asks, are there plans to use typed parameters syntax in function signatures?
I'm not sure exactly what the question means, but
Okay.
if it's parametric types, there are plans. Some languages, when you call, some typed languages, when you call a function, you can instantiate the parametric types explicitly. That's not something that we plan, but I would need to understand a little bit more. But parametric types is in the roadmap. It's something that we're going to have. Yeah.
All right. Vasilios says, I feel like the shortcomings of Elixir are structs, as they are also maps, which makes them flexible and unstable. Would typed structs make their definition/usage more strict and reliable?
Well, citation needed on the first part. But yes, the goal with typed structs is that we'll be able to understand exactly the types of each field and carry that out throughout the program, right? So you can spot bugs sooner, as we have been doing. Yeah.
All right. All right, Alex asks, if expressive types add a complexity/boilerplate burden, does AI change the trade-off?
That's a good question, and I think that, so my take on AI, which may change, so because we don't know where AI is going right now, but my take is that we still need the human in the loop. Maybe that's not going to be true in a year, and then I would change my position. But because we need the human in the loop, we still need to optimize for the human. So, at some point, even if AI is writing it, I assume that, even if we add all this expressiveness, it's going to be harder for AI to figure that out, right? And we'll have to jump in, we'll have to debug, and that's going to become our problem, and we don't want to deal with that complexity. So the short answer is I'm still optimizing for humans.
All right, great. Dominic asks, will structs ever natively implement the access behavior so we don't have to use access key, etc., in get in?
No, they won't. Yeah, there is a very well-defined reason why they don't do that. The access behavior, it's very, okay. So so we have been talking a lot about precision, right? And saying, look, we want to be precise. The thing is that if you say, look, if you use the access syntax, if you do X, open brackets, A, close brackets, what is the type of X? It can be a lot of things, right? It can be a keyword list, it can be a map. And now imagine that we started implementing it for every struct in your code base, in your dependencies. The type of X is going to be massive, right? And it will be very hard to figure out what X is, right? So the access behavior brings polymorphism, but if you make everything polymorphic, trying to understand what that program does for the human or the type system gets very hard, and that's why we don't do it. And that's why we won't do it. Yeah.
Okay. And Miguel asks, what's the status of expert?
That's a great question to ask the expert team.
All right.
Yeah.
Very well. All right. Ricardo asks, what percentage of your code got written by coding agents in the month of April?
Oh, very good. Yeah.
That's a good question. I like that one.
I can't say. No. Yes. So I would say that it changes. Where is Chris? He's not here? Oh.
Oh.
Yeah. So I have to say it. So I would say I use coding agents daily. So we be having. So the thing we have. The reason I asked the question at the beginning is because it has been a topic of discussion between Chris, myself, and other people. So we have been talking a lot about that the last days. And so what happened yesterday is that I had to implement a feature in DB connection. So if you use Acto, if you use any database in your applications, you use DB connection. And I had to implement a feature. Chris will likely disagree with the way I'm describing the facts, okay? But so I had to implement a feature in DB connection. So I started implement. So I looked at the code base. I understood the code base, so I could write the spec for the coding agent. And then Chris triggered the coding agent on his computer, and I implemented the feature on my computer, and I was faster than Codex. And not only that, my solution was, the solution that Codex came up with was 4 times bigger, okay, in terms of code. Yeah. So we had a lot of discussion from this, and one of the things is, so the reason that I'm bringing this up is because like there is some work. So when I'm using when I'm doing work on a Phoenix app, for example, I use Tidewave and I'm using coding agents a lot. And I would say there would be more than 80% of my code. But then there are things like when I'm working on something like DB connection or when I'm working on the type system, it's like I know that using the coding agent would only slow me down for now, so I don't use it for those problems. So if I had to say, it would be like 50%. That would be where I put it, because depending on the type of problem that I am working on and trying to solve, I use it all the time, but then there are some problems where, in my experience, and it's not like for lack of trying, I actually try. I tried yesterday and proved my point that for certain problems, it is not there, and me just going and doing the change is going to be quicker. Yeah.
All right. And Joe Henderson says, when will Valim LLM arrive?
Yeah.
It's nice typed out. Valim dash.
Yeah.
LLM.
It's yeah. Yeah. Yeah.
To be determined. All right, everybody, let's give a round of applause to José Valim.
Thank you.